slides. I'm still not very good in master slides, so mastering slides. So let me go back to what I do good at. So this topic basically about the principal stresses, principal directions. And so the first one, we know that for principal directions, that means in that direction, the shear stress equal to 0. Okay, so that is the definitions. So to calculate this one, then we say to determine one of the principal directions, and then you say n, okay, and L1, L2, L3. So here we're going to determine this one. Then basically graphically we can try is this. So this is the x1, 2, 3 directions. So in that particular orientation, let me try to draw it. So that is the inclined plane in such a spatial orientation, and the n is the uninormal vectors. N is here. So here n is the uninormal vectors. So in which here we specify square equal to 1. Okay, so here indicating any uninormal vectors. So n has the coordinate, the tip here, that has the, okay, that orientation of n. So here we are given the status of the stress in the x1, x2, and x3 coordinate. Okay, those are the given. And so that means, let me make one example here. So for example, in x1 plane, so this one is the x1 plane, right? Okay, that has the, although it's in the back here, but this is x1 plane, and on which it has the 3 components. For example, normal to the plane in the x1 direction, that is what we know, the tau 1. On this plane, and pointing to the 2 direction, so that is 1, 2, and here is 1, 3. So here I kind of using kind of the earthworm, that one just indicating I'm working on that surface. Okay. And then the other plane, x3 plane will be at the bottom here, x2 plane will be in the other side there. And to make that brief, I don't need to draw everything. Okay, so for example, you have this one, then let me erase this one because I don't need this. And so from the given information, and in any inclined plane, we know we are able to calculate the Cauchy stress, and that one is calculated by this T and Q and T and 1 and also T and 3. So the basically that is the reaction force in the inclined plane, in the inclined surface or inclined plane, in the surface. I think surface will be good. Surface, that means geometry was limited with confined boundary. So I would say here surface, okay. inclined plane, a plane is the plane anywhere that has in the same direction, but here the surface, that means here I specify in this triangular, okay? In the inclined surface of unit area, okay, so here I specify for my order calculations, everything will be referred to the inclined surface. I define that area equal to 1. If you say, why not I set up that area equal to any number other than 1, that's okay. Everything will be referred to relative to that one. So everything later on will be just ratio. That ratio will be cancelled out. So for here, we can using the unit area, okay? So basically here, we're indicating that is a directional force happen in there. And that directional force is in equilibrium with the given stress. Okay, so that is the physical meaning of this quantity. So here we already know that the Tn1, for example, we can calculate Tn1 and basically Ti is equal to Lj tau Ji. Okay, so that is our formula here. So, okay, we leave it that one here. So that is these given informations. On the other side, let's work on the definition of what is principal directions. In the principal directions, again, we work on the same coordinate system, and we work on the same inclined plane. So, okay, L1 to C. So in such a particular inclined plane, if this plane is one of the principal, if n is one of the principal directions, so that means in any plane normal to such a particular n, there's a no-shin stress. So let me draw the distribution of the stress on this inclined plane. So in this inclined plane, let me highlight here. One of the principal directions. Then only normal stress is in this plane. Okay, and let me normal stress, let me say that is sigma. Okay. So in this way, let me draw the normal stress. So the normal stress is a stress normal to that plane. So normal to that plane, that means that normal stress is in the n directions. So let me draw it. In certain magnitude, sigma. Sigma is the principal stress. Okay. So here we say this, which is one principal stress. Okay? One principal stress. Be good? So this is the given this is the derived information from the given the data here. This is the definition from the principle, from the definition of the principal directions. The two things, if n is one of the principal directions, then whatever the stress happened in the inclined surface must be the same. If we want to proceed the calculation, we stick with such a statement. If n is one of the principal directions, then what happened on the inclined plane, the forces must be the same. So let's work on this. Okay. So this direction force on the inclined plane is in terms of the 3 components in x1 to 3 directions. To make our calculation feasible, my job is to decompose such a sigma, which is in a particular orientation. I want to project sigma into x1 to 3 directions, such that the 3 components I can compare to actually equal to each of the components, right? Because I want to make them equal, because they are coming from the same given information. So let me try this. So stick with that kind of statement, and right now I'm working on is to work on how to project these particular vectors into x1 to 3 directions. So let me draw that again. So x1, x2, x3, and that particular force is this one. Okay, sigma, and sigma is such that it has a magnitude and in this unit directions. Okay, and in terms of the label, we can do this one here. This one graphically draw the projection is this. Okay, so that means this quantity represent its projections into x1 direction, right? So what is that amount? This amount is equal to sigma times
cosine x1.
Cosine,
Or, no,
for example, say, let me say if this is alpha, then that should be times cosine alpha, right? But here we are not given alpha, so this
L1.
doesn't work, so that is L1, because here we are given L1. Good, okay, and this quantity is the projections into L2 direction, so that one basically is equal to sigma times L2. Okay, the vertical one, that's the projection into 3 directions, sigma L3. Okay, so now, because this one is from cutting from the same free body diagrams, and the 2 are equal, so here you can make the equal very easily. So that means Tn1, so therefore here for making calculation, Tn1 must be equal to sigma L1, right? Tn2 equal to sigma L2, Tn3 equal to sigma L3. So that is our calculations. Solve them for L1, L2, L3, and sigma. In the 3 equations, we have 4 unknowns, and 3 of them are for direction n, and 1 is for magnitude of sigma. So 3 equations, 4 unknowns. In theory, this is we can at best find a relationship, but no unique solution in terms of our algebra, the non-real algebra. But actually, this form can be solved by solving the eigenvalue problem. So to this moment, the remaining job will be simply the solution process. Before we go to the solution process, any questions about the physical formulation here?
Sort of a comment. Before I was having trouble with the notation, the force notation for T of n.
Okay.
But T of n, you're just speaking about n being the normal vector for the plane that we're talking about.
Yeah, this one just simply is to label a specific.
Right, exactly.
Yeah.
And
that's it. Okay. So now let's implement this one in more detail. So in detail, let's do it here. What is Tn1? Let's apply to this one here. Tn1 equal to Lj tau J1, so that is L1 plus L2, 1 plus L3, 1. Okay, on the other side, this one equal to sigma L1. Okay. to make a replacement. Those ones are based upon our formulations. On the other side, I want to replace this and this by tau 1, 2 and about tau 1, 3. And such a replacement is due to because the tau ij, we know that the equal to tau ai. So which means tau is symmetric. Okay, in terms of the magnitude, tau 1, 2 equal to tau 2, 1 in magnitude. So we use the symmetry of the stress matrix. So that means in terms of the magnitude, they are equal. So I can do such a replacement. Okay, so in this way, let me rewrite this one. So the same thing, and L1 tau 1, 1 plus L2 tau 1, 2 plus L3 tau 1, 3 equal to sigma L1. Okay, so that's the first equation. The second equation, we repeat the same process. Tn2 equal to Lj tau j2. So L1 okay, this one again, let me take the symmetric and swap this number. Okay, and that one equal to sigma Lt. Okay, the third one. The same thing. Let me swap this one. Okay. So right now we have equation 1, equation 2, equation 3. And let me express the equation 1, 2, 3 into a matrix form. So the matrix form will be expressed in terms of this one. Unknown vector L1, 2, 3. Okay. And equal to on the right hand side L1, L2. Not here. Let me do this one. Sorry. So equation 1, 2, 3, and let me do one more replacement. So I'm going to move the right hand side into this the left hand side. Okay, so how to do that one? So I'm going to move this one to here. So basically that one becomes tau 1 minus sigma. Okay. So this one becomes 0. The same thing, I'm going to move this one to the left-hand side, so that means these have going to combine with this term. So this is tau minus sigma. The third one, again, this one going to move to the left-hand side, combine with this one. So that will be minus sigma. Good? Okay. So now we have three equations. Let me put into the matrix form here. L1, L2, L3. And the three equations, basically this is the 3 by 3 matrix. Right hand side is 0, 0, 0. This one, the left hand side is this. The first equations basically is these. The three elements multiply individually with the three variables should be equal to the first equations. So that means that 3 elements can be observed here is tau 1, 1 minus sigma, tau 1, 2, and tau 1, 3. Right? Okay. Then again, from the second equation here, multiplication of the 3 elements will be equal to this equation. So that means the 3 elements are the 3 here. Okay, so that we copy here. Tau 2, 1, tau 2, 2 minus sigma, and tau 2, 3. Okay, and you can repeat the same process in the last one. Tau 3, 1, 3, 2, 3, 3 minus sigma. Okay. This one, basically, on this side, we're working on is the details, how to solve for that equations. This one is the eigenvalue problems. And here maybe will be worth it for us to quickly review what is an eigenvalue problem and how to solve for it. And let me try demonstrate the process using a simple one. I don't have a preparation, but just let me make up one. Okay. A quick review of the eigenvalue problems. Eigenvalue problem starts with this. We are given a matrix, a square. Usually this one can be also applied to non-square matrix, but here we don't have to go that far. A square matrix A, for example, n by n. That is dimensions. So it's the eigenvalues of A equal to, say, lambda 1, lambda 2, and lambda m. For n by n dimensions, we should expect n eigenvalues, okay? And in general, those values can be distinct from one from another. But in certain special conditions, which means the certain arrangement and the content of A, it might be the eigenvalues can be repeated, okay? Can be repeated. And for majority of the engineering applications, and all the eigenvalues should be real numbers. Okay. In mathematics, that could be complex conjugate, but that's the different things we will cover here. The eigenvectors of A, and let's say the vectors x1, x2, and etc. x3. And each of the eigenvectors has the form. For example, say x1 equal to, it's a column vector, say so many elements. Okay, so there's an n by 1. So here is not 0. Here I'm just indicating is a content, is a column vector, and has the n components. So each of the eigenvectors, basically that really is a vector, and something like this one. Okay. The eigenvalue problem is this. We are given A. We're going to determine to find the eigenvalue and eigenvectors by solving this. Ax equal to lambda x. By solving this equation. Okay. And this equation basically here is this. A has the dimensions n by n. and x has a dimension n by 1, and lambda here is x is n by 1. Lambda is a scalar. Okay, so here in general, we don't know the value yet. We simply use lambda without any subscript. And for indicating that is one of such eigenvalues, we're using x without any specific subscript to indicate that is the indicating one of possible eigenvectors. So in general, we write in this. And the solution process, how to solve for lambda and x, is this. The step 1 is we rearrange this one. Basically, this equation, before proceeding to step 1, let me make a mark. This one representing is an n set of linear equations. Okay, so for example, let me try such one example. Say if A equal to ABCD, okay, and let me say x will be equal to x1, x2, and equal to lambda and x1, x2. Okay, let me make one simple example. So this one basically once we expand it, and that one really represent is ax1 plus bx2 equal to lambda x1. Then this is cx1 plus dx2 equal to lambda x2. C, that one representing is the two linear equations. Okay, so keep that in mind. This one have the, if we expand it, there's so many terms, and then even longer. For this one, that will help us to understand I'm going to write on the step 1. So let me rearrange this one. So let me move the x1 term, combine everything, merge everything to the left-hand side. So basically that becomes, the first equation is a minus lambda, x1 plus bx2 equal to 0. The second equation becomes cx1 plus d minus lambda x2 equal to 0. Okay. So from here you can see this form pretty much match to our form here. The sigma, the raw sigma here, that pretty much is the one of the eigenvalue lambda here. Okay. So this form basically we can rewrite into this a minus lambda and b c d minus lambda x1, x2 equal to 0. Okay. And or otherwise, and let me utilize the symbols. Or otherwise, this one can be like this: AB, CD minus lambda 0, 0 lambda x1, x2 equal to 0, right? Compared to our symbols, let me define this is our matrix A. So this is our matrix A. And this term basically is lambda times I. I is called the identity index, identity matrix. I, for example, for 2 by 2 is, sorry, not identical, the diagonal, unit diagonal, okay? For example, if I is 3 by 3, then that is 1, 1, 1, and 0, 0, 0, 0, 0, 0 here. Okay, so basically here, this is the, for example, for this case is 2 by 2. And then this one becomes, let me call using the x vector. So let me define this is the x vector equal to 0. So basically from this equation, step 1, we can easily write is a minus lambda times I is an n by n index, and then x equal to 0. Okay? Using this simple example, that should be easy for everyone to comprehend these things. Then step 2. We solve, the first one we solve for eigenvalue. Lambda by taking the determinant of this matrix equal to 0. To this moment, let me utilize one example here. So in this way, let me use a number. Okay, let me make this one. Let me erase this portion here. So let me make one example and compare. So say if A equal to 1 minus 1, 0, and 0, 2, 1, and 0, 0, minus 1. Okay, this is not a stress matrix. I simply review the eigenvalue problem, so this one I just pick one here. Okay, so to find its eigenvalue, eigenvalue, eigenvectors. So here we determined A minus lambda I index equal to 0. So that means that indicating determinant of this matrix 1 minus lambda minus 1, 0, 0, 2 minus lambda 0, 0 minus 1. Okay, the first one you need to operate the algebra on two matrices. This is A and minus lambda. Lambda times I, that means lambda will appear on the diagonal term, so that becomes like this. Okay. So now come to the determinant of a matrix. For 3 by 3 matrix or lower dimension, we can do it by hand. For higher dimensions, then there's a formula there. But here we can do this one. So determinant of 3 by 3 basically is a combination of these. Look at this carefully. Here, multiplication of the 3 terms plus multiplications of 1, 2, and this one, let me go this way. And also multiplication of 1, 2, 3. So let me go this way. Okay, so that means is 1 minus lambda, 2 minus lambda, minus 1 minus lambda, and 1, 2, 3, this term equal to 0, the other 3 term equal to 0. Then minus multiplication of these 3 terms, and multiplication of 1, 2, these 3 terms, multiplication of 1, 2, 3 terms. So that means 0 plus 0 plus 0. Good. Okay. So I use color to label the calculations, and don't ask any questions. If you have any questions, go back to your high school. Okay, to see how to determine how to calculate determinant of a matrix. Okay, so under this one, then here this is a special pickup case. So under this case, we can see easily lambda equal to 1, 2, and minus 1. We have 3 eigenvalues, right? And for each eigenvalues, now, and suppose you will obtain lambda 1, lambda 2, and lambda n. Okay, just like our calculations. Then step 3 is for each lambda I and I equal to 1 to n, solve for the form solve for xi by this a minus lambda. Okay, so that's a summary. Let me do this one here. So for this one, for example, say for each of the lambda, so for lambda equal to, say, the first one equal to 1. Okay. For lambda to 1, then we go back to original ax1, ax equal to lambda x. That is our original statement of the province. For lambda equal to lambda 1, so that means ax equal to lambda 1 x, and here the x corresponding is the eigenvectors associated with the first eigenvalue. So why not here we simply put the label here that indicating that is the first eigenvalue, first eigenvectors that associated with this particular value. Okay, so with this labeling in place, then basically we can implement is this. And for a minus lambda x1 equal to 0. Okay, so that means is we plug into here a minus lambda I. So that is 0 minus 1 0 0 1 1 0 0 minus 2. Okay, good. So from here, this is a vector of such an element. So here, if you like, really you can come up with any symbol. So here, let me replace the first eigenvectors by such a label. Say, for example, let me make x, y, okay? And here, that the first one indicating that is the first eigen vectors. Okay, just for labeling. Okay. So now we want to solve for this one. Then you can see. We'll try to solve for it, see what happens. So basically, this one, once we expand it, that representing 3 equations. For the first row here, that representing is minus y equal to 0. Then we expand in the second row, that indicating is y plus z equal to 0. And these are expansions of the first row, then the second row. Okay. And from here, so that means z equal to 0. Okay. The third one, let me expand it. The third one basically leaving in z equal to 0, redundant. Good? Okay, so right now for our case, we want to solve for the first eigenvectors, and that has the value. The y and z are equal to 0. The first element is undefined, no, unsolved yet. So that one, this can be arbitrary constant. So let me say this is arbitrary constant. Let me just use alpha. From these 3 equations, we don't know the value for x, right? It's arbitrary. For arbitrary reason, we simply say it's alpha or anything. And usually, that's representing is alpha 1, 0, 0. So that means from here in this, you can see the ratio of the elements inside the first eigenvector. The ratio in such a vector is in this form. we don't know exactly the value yet, but we know the ratio among each element. So the eigenvectors is a vector that really is a spatial relations among each elements here. But we won't be okay to know the exact value. At most, we know their ratio, their relations, and that meaning the eigenvectors. So here, in general, we can say the first eigenvector is this one. If you like, you can simply express that is the ratio, is the relation. So basically, the eigenvectors representing is the relations among the elements there. So this is the first one. If you like, we can identify this is the first eigenvectors. For the second one, we may continue. So you can continue to write. So let me do this one here. So the second one is lambda 2, and lambda 2 equal to 2. Okay, so here let me modify everything that is 2 here. Okay, and that one corresponding is 1, 1, 0, 0, 0, minus 1, 0, 0, 3. And this one will be the second. Okay, so element A matrix multiplied diagonally is simply minus 2. So minus 1, 0, minus 3 becomes, okay. So for this case, we're expanding those equations. Expanding the first equations, and that one basically becomes x plus y equal to 0. The second equation gives us z equal to 0. The third one gives us z equal to 0 redundant. Okay. So for this case, we come up with is this. This one basically that means y equal to minus x. Okay. So the second vectors have such a relation that is x minus x0. Right? So again, we don't know the value of x, but at least we know the relations is y minus 1 and 0. X is any numbers here. So here we say the second eigenvectors, again, relating the, in terms of portion, we know their relation is fixed numbers. So this is our second eigenvector. Okay? Good? So in this way, for this problem, we're going to solve for sigma using the same procedures. If you solve for eigenvalues, that is our principal stresses. And you solve for the eigenvectors, and that is a relation, and that gives you is the L. For example, say if this would be, say, second eigenvectors, and that would be this one, but remember, in our formulations, we normalize eigenvectors. In all of our lecturing, I like to normalize, have this one be normalized. So for whatever the eigenvector you solve for the principal directions, please normalize it before turning your answer. If you wouldn't normalize, then everything, all the related calculation, you will have certain constant ratio difference from the whatever it's supposed to be. Okay, keep that in mind. So in this way, by implementing the kind of the things for the third one, that shouldn't be hard. If you like to run MATLAB, the MATLAB is this. You give an A matrix, for example, you type in the A matrix like that one, and then you simply using eigenvector, this command, EIG, then that will give you the result. Even furthermore, here you indicate, for example, this is a L, this is B. I believe once you hit return, this will be a matrix, this will be a matrix. I forgot which one is which one, but for example, the first one will be eigenvalues. Then, for example, the eigenvalue appeared. Once you hit return, then that should be certain numbers. For example, for our example, could be say 1, 2, and minus 1. okay, something like this one. It would say L equal to this, okay, and it will give you V equal to something. The first column is the vector corresponding to this, and the second column is the vector the eigenvector corresponding to this, etc. However, MATLAB depends on versions; they are not normalized. So keep that in mind. Do it by yourself with one step. Okay. So next.